Well, how do we calculate the equilibrium constant? The most direct way is to do the reaction and measure the concentrations of all the reactants and products at equilibrium, which sounds easy, but actually is a little bit challenging. But doing the problems is great because they just tell us what the concentrations are. So here we have this H2 plus I2 making 2 high. Suppose that we have these concentrations. H2 is 0.11 molar, I2 is 0.11 molar, and the HI is 0.78 molar at equilibrium. This is at 445 degrees Celsius. Calculate Kc. So we're going to write the equilibrium expression, and then we're going to put the concentrations in and calculate. So Kc is equal to the concentration of HI squared, that's our product, divided by the concentration of H2 and the concentration of I2. So we have all of these values here, concentration of H2, I2, and HI. We just put the numbers into the expression. So HI is 0.78, and that gets squared. In the denominator, we have 0.11 and 0.11. Yeah, so with two significant figures, it'd be 50 with a decimal point, or it'd be better to write it as 5.0 times 10 to the 1.
So is this considered small?
That would be considered
I don't know.
close to 1,
Okay. Oh.
right? Compared to 10 to the minus 31 or 10 to the plus 26, right? 50 then, pretty close to 1. Yeah, so this one's going to be, there's going to be significant amounts of reactants and products at equilibrium.
Okay.
And if we, just look at these concentrations, we can see, well, these are smaller than that, but they're in the same ballpark, right? Yeah. Any other questions? Why did they say at 445 degrees C? Because the temperature affects the equilibrium. We don't use it in the calculation here, but if we're going to compare this reaction to something else, we have to compare at the same temperature. So here's some other data for this reaction, same reaction. So here we're starting with half molar of the reactants and none of the products. And at equilibrium, we get the values we were just given, and we calculate the equilibrium constant as 50. If we start with no reactants and half molar product, we end up with these values, put those in, equilibrium constant is still 50. Start with equal amounts of all three things. At equilibrium, you get this. Equilibrium constant is still constant at 50. Start with twice as much H2 as I2 and no product, still 50. Reverse that is still 50. The equilibrium constant is constant and it has nothing to do with the initial concentrations of anything. Any questions? Well, what if we don't have all of the equilibrium concentrations? If we know the initial concentrations, and usually we can know that because we are controlling that. We're putting that in. It's like I'm going to put this many moles and it's this volume. I'm setting it up that way. Initial concentrations. And if we can measure the equilibrium concentration of one of the reactants or products, then we can figure out what the equilibrium constant is. So let's look at this example, nice simple example. Here we have reactant A is in equilibrium with product B, and A forms 2 moles of B. Initially, we have 1 mole per liter of A and none of B. So then this is called an ICE table, ICE, initial change equilibrium. And we're going to be using ICE tables a lot. So class, I'd like you to meet the ICE table. ICE table, this is my class. Introductions, right? Well, what's going to happen with this equilibrium if I've got reactant and no product? It can only go forward, right? And so the concentration of A is going to go down, and the concentration of B is going to go up. But I don't know how much. I'm going to call it X. I'm going to say that X is the amount, the concentration that A goes down. It goes down by X. So if A goes down by X, so I lose 1 mole per liter of A, I gain 2 moles per liter of B. So the change in A is related to the change in B by the stoichiometry of the chemical reaction. So B is going to increase by 2x. The 2 here is this 2 over there. Everybody with me on that? You okay with that? Well, the equilibrium concentration of A was measured. So the initial plus the change has to equal the equilibrium concentration. What's X? 0.25. So X equals 0.25. So B then must have increased by plus 0.5. So its concentration at the end will be 0.5. Questions?
Why is it a negative for the concentration of A?
Why is it a negative? Because we're losing concentration of A. The reactants go away, their concentration goes down, and the products increase. Sometimes we're not sure which direction, but this time we don't have any product, and so it can only go forward. Yes?
Say we were trying to solve, we were given the equilibrium for B, would it be like 1.00 plus X? Because you're creating the product. So that little equation over there to the left side.
Right, so if we had 1.00 of B and none of A,
Right.
well then we'd have to think, well,
What I'm saying is it's 1.00 minus X because A reactant is decreasing. Correct?
yes, yes. So I used my starting concentrations and the 1 equilibrium concentration and the stoichiometry of the balanced chemical equation to figure out the equilibrium concentration of the other things. You had a question?
Well, now I'm thinking, because of what she said, if you start off with B, maybe because you're going backwards, would
Mhm.
B be negative 2x?
Mm-hmm. So, yeah, if we started with only B and none of A, we would know that the reaction is going to go in the reverse, and so we could set it up and say, well, it's minus 2x and plus x. Sometimes it's not obvious which direction it's going to go, and so you just set it up one way, and if you pick the wrong way, all that's going to happen is your x value will be negative. And you put it in, and it all works out just fine. And we're going to learn about another thing that will help us to predict which direction things are going to go.
So the equilibrium constant 1/3.
Yeah. So the equilibrium constant then is the concentration of B squared over the concentration of A. So we have 0.75, nope, 0.5 squared divided by 0.75. Which equals 0.33, or 1/3. Any questions?
When you get a number like that, is
Mhm.
it important to give the ratio so that you have a precise number, or should you use decimal?
That's a good question. Should I say 0.33 and go with sig figs, or should I say 1/3 and be more exact? Well, the thing is, these are measurements, and they do have just two significant figures, and so I would just go with the decimal equivalent. It's always helpful to carry a couple extra digits until you get to your ultimate destination to avoid rounding errors. But yeah, any other questions? Okay, let's do one with actual compounds. The reaction shown between carbon monoxide and hydrogen is carried out with initial concentrations of 0.27 and 0.49 molar at equilibrium. The methanol concentration is 0.11 molar. Find the equilibrium constant. So we need to make an ice table. I like to use the balanced chemical equation as the top of my ice table, and so that labels my columns. So this is going to be the column for CO concentrations, for H2 concentrations, and for CH3OH. So I just start ice. So my initial concentration for CO, 0.27. For H2, 0.49. Now, it's not telling us anything about the initial concentration of CH3OH. What do we do? Well, what's often true when you mix reactants and you have a reaction happening? You get products, but was there product in there to start with? No, because you're trying to make it, right? So you didn't have any. So if it leaves out the product like this, you can assume it's 0. So the initial concentration of that product is 0. Now it says at equilibrium, CH3 is 0.11. CH3OH, 0.11. Well, let's figure out what's going to change here. I'm starting with all reactants, no products. My reactants are going to decrease in concentration. My product is going to increase in concentration. It's simplest if you let X be the change in something that has a coefficient of 1, right? So if this is decreasing by X, then H2 is decreasing by 2X. And CH3OH is changing by plus X. Everybody okay with that? So over here I have 0 plus X is 0.11. Well, that pretty much tells me what X is, right? X is 0.11. So here, 0.27 minus X, that's 0.27 minus 0.11. That's going to be 0.16, right? And this is going to be minus 2X, which would be minus 0.22. And so that's going to be 0.27. I can tell from facial expressions that some of you have questions. Ask.
So all three of those are the equilibrium constant?
No, these are equilibrium concentrations.
Okay.
And then we'll write the equilibrium constant expression and put them into that.
Oh, yeah.
Yeah.
Okay.
That was a great question. This ice table business is really important in Chem 1B. And this is the beginning of it, and so this is the part where you have to ask questions until it makes sense.
So C and E are the same, we just know the formula for the first two, so we're trying to.
Well, C is how much the concentrations are changing.
Okay.
So what we're doing really is we're inferring what happened based on this one equilibrium concentration. If that was 0 and now it's 0.11, this must have changed in that it increased by 0.11. If this increases 0.11, for every 1 mole of this, I lose 1 mole of that. So if I'm increasing 0.11 moles per liter of this, then I'm losing 0.11 moles per liter of that. And this has a 2 in front of it, so I'm using twice as much.
That's the -2.
Yes, this is the 2. The negative is because those are reactants that are going away, their concentrations are decreasing. The 2 is the coefficient.
So will we always start out with X's on the chain?
X's are usually going to be in the change, yeah.
Okay, so
Should it always equal the subtraction of the reactants? Will it always equal the product?
Will these combined always equal that? No. No. It depends on all kinds of things. Yeah, that's a good question. But we're taking the initial and adding the change. Change can be positive or negative. And we're getting at equilibrium. So we found our equilibrium concentrations. We're not done yet because it says, what's the equilibrium constant? So the equilibrium constant, I write that expression that we were feeling pretty comfortable with. CH3OH divided by CO and H2 squared. There's no liquids or solids in there, so we're good. So then this is the equilibrium concentration for CH3OH. So I put that in there, 0.11. And the equilibrium concentration of CO is 0.16. And for H2, 0.27, and that one is squared. So the equilibrium constant is 9.4. This is a much more practical way to find an equilibrium constant rather than just measuring all of the equilibrium concentrations, because that's hard. Any questions?
What's hard?
To measure equilibrium concentrations of all of the reactants and products without disturbing the equilibrium.
How do they do it?
Well, you could set up as many reactions as you have reactants and products so that you could measure the reactant in one and the product in another and the other product in another. You still have to be careful though, because some of your detection methods might mess things up. Yeah. So this way, you just have to find one thing that you can measure, and then you're good. 9.4. Reaction shown is carried out with an initial concentration of CH4 equal 0.087 at equilibrium. The H2 concentration is 0.012. Find the equilibrium constant. So ice, initial change equilibrium. I'm going to take the numbers that they gave me and put them in the appropriate places. So the initial concentration of CH4 is 0.087. It doesn't say anything about the products. What can I assume their concentrations are? 0. So this is 0, and that's 0. And then it gives me one equilibrium concentration. That's for the H2. So this is 0.12. Nope, 0.012. So now we kind of have to decide, well, what is X going to be? Because if I say that X is the amount that the H2 is changing, then it gets a little awkward with the coefficients and stuff with everything else. So I'm going to pick something that has a coefficient of 1, or I'm just going to use this 3 and say, well, this is increasing by 3x. And then I can use x and just stick the coefficient in front of it, and I don't have to think very much. So this is going to be 2x, and that's going to be x, but those are going to be, that one's going to be negative, and this one's going to be positive. Because, well, let's see, I'm going to move this over. There's my product reactant line. And, you know, if you want to draw boxes,
So then what should you do? 0, 1, 2, 3.
yeah, so then we can figure that x must be 0.012 divided by 3. Because 0.012 is equal to 3x. So x equals 0.012 divided by 3. X is 0.004. So x is 0.004. Here I have 0 plus x. So what's my equilibrium concentration of C2H2? 0.004. And here I'm losing 2x, right? So I've got 0.087 minus 2 times 0.004. This is the sort of stuff that you wouldn't really write down necessarily. And this stuff over here, you wouldn't necessarily write that down. You certainly can, but you don't have to. So I'm getting 0.079. Any questions? And then we have to calculate the constant, right? K equals C2H2 times H2 cubed over CH4 squared. And then make sure that you can get from having this written on paper to your calculator giving you the correct answer. Because there's a number of holes you can fall into there.
So is it 1.1 times 10 seconds?
Mm-hmm.
And that's still considered.
That's considered small. I mean, it's not really small, but it's pretty small.
What was the other one? 50.
It was 50
And you said that
or
was-
9.4. Those are like middle. Yes.
So I plus C should equal E, right?
I plus C should equal E. Yep.
And then, why are we plugging in those numbers to it? Are those, is the E values, those are concentration?
Yes.
At equilibrium?
These are the equilibrium concentrations. We have the initial concentrations. We have to know the initial concentrations of all of them. And then we need the equilibrium concentration of just one. And we could figure the rest out using stoichiometry. So we figure out all the equilibrium concentrations, then we put them into the expression and we can calculate the constant. Any questions? 1.1 times 10 to the 6.